Okay, lab 4. So let me go over. So I think the first part of the lab's pretty self-explanatory. Walk through the worksheet. It's posted now. There's screenshots there to help you. Having done the week last week and familiarizing yourself with the PhET simulations, I think will make this week pretty straightforward, except for the last part. So we want to measure the internal resistance of a power supply. So let me spend a few minutes going over that. There is a video where I walk through that, attached a link to a video where I walk through that in the lab write-up. But let's go through it quickly. And then probably the best use of your time this week would probably be study for the exam. And then the exam is Friday, and then Friday afternoon, Saturday, Sunday, spend time on the lab and turn it in Sunday evening. Okay, that'll be the due date, and I think that makes more sense. We can also spend some time after this. I'll finish up what I'm doing with the lab for this week, and I'll stop the recording, and then I can hang around and do like an office hour here if people want that. Okay, so what happens with a lot of our electronics, we kind of have this ideal version of all of our electronics. So we've talked about the fact that, I think we've talked about it, maybe not so much. A voltmeter, when you hook it up to something, you're trying to measure the voltage across that device, across that resistor, and you're assuming it's the same as the voltage across that resistor when the voltmeter is not hooked up to it, right? That's the whole point. You're trying to determine what the voltage is across that resistor, but when you go and hook up that voltmeter to the resistor, you might actually be changing the voltage on that resistor. So, and there actually is a law in physics that says you can't measure something without mucking it up first, without disrupting the system and changing what you're measuring. So, so that's what happens with this. If we know the voltage across that resistor, I'll call that point A and that point B, right? We know that delta VAB is I times the resistance, whatever the current is through that resistance times the resistance. So if you put a voltmeter here and some of the current that would normally go through that resistor now can split, and part goes through the resistor and part goes through the voltmeter, then you've just changed the voltage, right? You're measuring a different value across that resistor than you're going to have when you remove the voltmeter and go back to your original circuit. So what can you do to prevent I2 from flowing through the voltmeter? You can make the resistance of the voltmeter really big. So you want a voltmeter to have a really big internal resistance. You want it to act as if it has an infinite resistance. So we say an ideal voltmeter has an infinite resistance. Okay, so the same is true with power supplies. A power supply, DC power supply like this one, when you see that symbol means it's an ideal power supply. It puts out a certain voltage. We use this script E. That stands for EMF. That's the voltage that the maximum voltage a power supply can put out. But in the real world, power supplies have some internal resistance to them. We try to make it small, but it always has to have some internal resistance. So in the real world, that's the power supply doesn't really look like this. It looks like this. Where this is the power supply. Right? Could be a battery, could be a DC power supply like we have in lab. whatever. Batteries have some internal resistance. It's low. It's 1, 2 ohms, something like that. But batteries have some internal resistance. And we would call this our internal and this the EMF. And this red dashed box, that's our power supply. And so when you hook up to your power supply, we have the terminals are right here, right? Or on a battery, the terminals are right there, the positive terminal of the battery and the negative terminal. That's where you hook up to your battery. But this red box is like us with our X-ray vision zooming in on the power supply or the battery and seeing that, hey, wait a minute, it's not just an ideal power source, it's an ideal power source in series with the resistor. So when we hook this up, so if there's no, this is our battery or our power supply. If we hook this up to an infinite resistance, right? If there's no, if this is an ideal meter, then it has infinite resistance, right? So no current is flowing. If no current is flowing, what is the reading on this voltmeter right now? Should we get out our pens here? If we're calling this 0 volts, one side is hooked up to 0 volts. Then this right here, I'll use blue, has to be whatever the battery is, right? If we started at 0 and we go through a 9-volt battery, then we have to be at 9 volts at the top of the battery, right? Whatever that battery is, or whatever that power supply is set to, I'm just calling it script E. So we have to be that much above 0. Now, what's the voltage drop across a resistor? I times R. So delta V across a resistor is IR. So if I is 0, there can't be any voltage difference across that resistor, right? It's kind of like a hose with water in it. If there's a pressure difference, water is going to move through the hose. If there's no pressure difference, then the water is not going to move. Or if we know the water is not moving, then we know there can't possibly be a pressure difference, because if there was a pressure difference, the water would be moving. So the same is true here. If we know the charges are not moving through that resistor, then there cannot be a potential difference across the resistor, because if there was a potential difference across the resistor, the charges would be moving. I don't know, it's kind of a circular argument, but it's that's makes sense in the end, I think, hopefully. So if there's no potential difference across that resistor, whatever it is on the bottom of the resistor, it has to be the same at the top of the resistor. And then this wire is just an equipotential surface. Okay, so what does this read? Oops, what happened? Oh no, come back. Now I have to share it with you again. Okay, this chat. Okay, I think we're back. So where's my, there we go. So this is all the same potential. And what does this equal? It's measuring the EMF of the battery. Okay. So that's called the EMF of the battery. It's the maximum potential difference the battery can supply. Because what's going to happen when it starts to flow current? Well, we'll get there in just a second. This is the EMF of the battery. This is what is labeled. So if it's a 9-volt battery, if it says 9 volts on the battery, that's the EMF of the battery, the maximum voltage the battery can put out. If it's a 1.5 volt battery, that's the EMF of the battery. But it's usually a little off from that value, you know, and it depends on how new it is and things like that. So we'll measure it. So you can hook this up, and that's what you've measured, the EMF of the battery. Now what we're going to do is take a look at what happens when current starts to flow. So when current is flowing, we hook up out here. Usually we call this the load. Whatever we're hooking up to our power supply is the load. It's loading down the power supply, right? The power supply needs to provide power to that object. Maybe it's a heater, maybe it's a light bulb, maybe it's a toaster, it's something, right? We're putting some load on our system. So now current is flowing. So let's think about our power supply. And we want to know what's the voltage across those terminals of the power supply. We call that the terminal voltage. So if we call this 0, let me get out my green pen again. If we call this 0, and this was the EMF of the battery. Now we have current flowing. So we're going to drop by some amount going through the internal resistance of the power supply, and we're going to be a little bit lower when we come out the other side. What color should I use for that? How about red? We're going to be a different voltage up here. So the voltage we see here is going to be what? It's going to be, let's go in the bottom here. Let's start here. We're going to go in the bottom. We're going to go through the battery and come out the top, right? So if we go in the bottom, we're starting at 0. We go up by the EMF of the battery. So that's why I have an E there. We've started at 0. We've gone up by E. And now what are we doing? We're going to drop by I times R internal. And then we're going to come out the other side, and that's going to be our voltage there, the red, what I'm using red to indicate. Did you follow that? You come in here at 0. You go through a battery, so now you're at plus E. You drop, you go through a resistor, so you've dropped by IR. So when you get up here to the top, you're E minus IR. So we could measure that voltage with our voltmeter. Where's a voltmeter? How about right here? We could measure that voltage with a voltmeter. And so this is going to be, I'm going to call that V terminal. And this is V terminal. So we measure it, and we know what load resistor we're putting on here. So we can figure out what I is, right? V terminal is equal to I times R load. You don't have to, I'm not taking roll. It's okay. It was just that 1 week I needed to do that. Okay, so we're good. So from this measurement, we know this. So we just measured, what did we measure? We measured this, we know this. So now we've just calculated what I is, right? So now we know I. And then we come up to this equation. I'll rewrite it down here. Maybe I should have told you what the whole point of this was. We're trying to figure out what our load is, what our internal is. What's the internal resistance of this function generator or the battery? So this is not load, this is internal here. Right, this just is this equation. I rewrote it here, okay? So we know I, this we know, we've measured this, we know I, so we can solve for our internal. So that's how we get our internal. Okay, it's a little tricky because you haven't had circuits yet, right? But I think once we have circuits, you'll go back and look at this and go, oh, yeah, that's not so bad. Okay, so the idea is we hook up a resistor that's a little bit less, a little bit more, and about the same as what our internal is. So on the PhET simulator, you can tell it to give the battery an internal resistance. So that's what you're going to do. You're going to set the internal resistance. Unfortunately, that means you know what the internal resistance is, right? But it would be nice if you had a friend come over and set the internal resistance, and then you do the calculation and see if you get it right. So we're assuming this is an ideal voltmeter. That's the only assumption we're making in all of this. Okay. Can you work in groups? Yes, but try to do, like last time I asked you to have each person to do their own data and use slightly different values. So then you can, when you tie it into one report, I've seen that you've kind of done it 2 times or 3 times with some slightly different values. So do the same thing here. Okay. So what I'm going to do, I'm going to stop the recording. And then you can make best use of your time. I'll stick around to answer questions. You can do the lab after the exam Friday or over the weekend, get it turned in by Sunday night. The lab's pretty self-explanatory. If you've familiarized yourself with the PhET simulation last week, the first part should be no problem. Just pointing out some things, some sticking points sometimes students have trouble with. What happens when you put batteries in series and parallel, things like that. So there's good stuff in this lab, but you could wait until after the exam. All right. So I'm going to stop this recording. And if I believe the best use of your time is